Sam, I seriously don't believe this. Look at this. You were meant to do this ages ago.
I did all of this yesterday. It's just you and Emily making so much mess that I can't keep up.
Bullshit! Look at this. This has been here for the last few weeks.
What are you talking about? This is clean. This is so clean.
Look, do you know what? I've actually had enough of living with you, to be quite honest with you, Sam.
Fine.
You just don't
Fine.
your weight.
Fine. You go then, and I will go my own way.
Fine.
Goodbye.
I will.
We are never, ever, ever getting back together. We are never, ever, ever getting back together. You go talk to your friends, talk to my friends, talk to me. But we are never, ever, ever, ever getting back together.
Hello.
Hello? What? What's this?
I don't know, you're sitting on the wall. I was
I
was just coming to see what's up, yeah?
Well, you see, it's my bloody Sam. He's always getting on my nerves. He never does the washing up. He's an absolute bloody nightmare.
I wouldn't worry, Benito. You know, these things happen in life. You know, you could be doing better things. You know, like making videos. I think that's something you might consider doing.
I suppose so, but I mean... Shit! The video! Ah! Right. Right, I'm calm now. Hello everyone, yes, it's the 4th episode of Acquisition of Behaviour, and as promised, we're going to be learning about learning today. So it's one of our, it's our second cognitive trait that we're going to dissect and look into in a bit more detail. So, to start with, we need a definition of what learning is. Right, I think that's a bit simple, but often you'll find there's the simplest words that are the hardest to define. So learning, in the way that we're looking at it, is a change in cognitive state due to experience. Now, when looking at animals, it's difficult to tell whether learning has happened or not. So what you do in the lab, you normally do lab experiments, and you usually have 2 groups. Now each of these groups experiences a different thing. So usually one is a control and the other one is trained in some way, for example, for it to learn something. And then both groups are put together, given the same experience, and then we look at differences between the 2 groups. So for example, canaries. Male canaries were reared in isolation or with other canaries. Okay? You could then put all these together, look at the individual canaries and see whether the ones that were reared in isolation actually learnt the calls of their fellow colleagues, if you like. Okay? And that's all very good, but that doesn't tell us really what type of learning is happening. Now before we go into that, we need to look at the 3 main dimensions of learning, and when you think about it, they're quite obvious, so let's go through them. So the first one, this is one that a lot of people overlook, which I'll explain in a bit, is the conditions needed for learning. Maybe a particular type of learning is only possible at a certain age, it's only at only a certain part of your development. And this is easily overlooked because these stages could be very, very early on. For example, ducks can only recognise the calls of the adults if they're exposed to the sound of their adults when they're still inside the egg. Okay, so before they even hatch. Okay, so there's very early sensitive periods in this sort of thing. Second one is the content of the learning, which basically speaks for itself, and repeated exposure increases the associative strength. And the third is the effects of learning. So what is the basic outcome of all of this? What is the point, basically? And the effects of this don't have to be straight away, they can be later on as well. For example, the marsh tit, which is a alright species of tit. Anyway, basically stores food. It caches it for later. Now, the immediate outcome of that, the overall benefit of the bird doing that, he isn't going to receive straight away, only when he's hungry. You know, when he's a bit peckish. Yeah, bird. He's got a beak, so he's peckish. Oh, okay. So he's learned that even if he's not hungry, he should still store the food. Now, one of the main types of learning is this thing called classical conditioning. And the real master, the undisputed king of classical conditioning, was a guy called Pavlov, and he's very, very famous. You might have heard of Pavlov's dogs, and that's exactly what we're going to be talking about, because that is the experiment which demonstrated classical conditioning. So imagine good old Pavlov in his, in his nice comfy home. Imagine there was a nice, nice ancient fireplace. Anyway, I don't know what I'm going on about now. But he had a dog, right? A nice Labrador, I'd imagine. He's a tasteful chap, right? So, whenever the dog smelt that Din-Din's was ready, that the food was ready, he'd salivate. Naturally, who wouldn't? It was probably, no cheap dog food, some high upper class dog food it probably was. So he was salivating. I'm not going to do it, I almost did a demonstration then. That would have been awkward. Right, so, and then what Pavlov decided to do, because he's a very sophisticated bloke, so whenever the food was ready for the dog, he'd ring a bell. Ding ding, right? And then what he found was, even if the food wasn't there, even if there was no food, if he rang the bell, the dog would salivate. So the dog has associated the sound of the bell with the presence of food. Right? Simple enough. Now we can attach a whole load of weird symbols to all of the things I just said. The unconditioned stimulus and the unconditioned response, and the conditioned stimulus and the conditioned response, and they're all represented by these symbols here. So US, the unconditioned stimulus, is the smell of the food, right? Because that is why the dog was salivating in the first place, right? The unconditioned response is the salivation due to the smell of the food, right? That's easy. The conditioned stimulus is the bell ringing, okay, because this is what he introduced after, and the dog eventually develops an association with the bell and the food. So that's what the conditioned response is. It's the salivation due to the bell ringing. Now the problem with this is that we can't always be sure that the behaviour we're seeing is explained by the conditioning. The dog could be salivating anyway, right? So Pavlov developed a nice experimental design to test to see whether the salivation was actually due to the bell ringing. So what you have three groups. So you have a positive control, so that's when the bell rings, there is actually food there, okay? The negative control is completely the opposite. So this time, the bell only rings when there isn't any food. Okay, so the Pavlov has been training the dog, so the smell of food, and when the food isn't there, he rings the bell. Okay, so there's never a time when the bell is ringing when the food is actually there. Because that's got to happen at some point, that is in the positive control, because otherwise there will be no association built between the two. Okay? And then we have this random control, which is all over the place. So sometimes the bell rings when there's food there, sometimes it doesn't. Sometimes it rings when there's no food there, and so on. So now the element of surprise is very important in this, and this probably explains this phenomenon called blocking. Okay? So you can have an experiment where you have a sound, such as a bell ringing, and the dog associates that with food, so it salivates, right? Now the association between the sound of the bell ringing and the salivation is so strong that, well then what Pavlov next did was, as well as the bell ringing, he shone a light, right, at the dog, right? But the bell was still ringing. But because the strength of the association between the bell and the food was so strong, if you just showed the light and no bell to the dog, then it wouldn't salivate. God, let me turn the light on. Now, alternatively, if you subject the dogs to the noise of the bell ringing and the light at the same time, so there was no strong association between the bell and the food beforehand, then if you only show the light, then you do get conditioning, okay? The dog does salivate, right? And this is all explained by this thing called the rescorla-wagner model, devised by rescorla-wagner, which I assume was some sort of mathematician, because it's a mathematical model explaining all of this. And there are a couple of symbols which are used, but basically, as the number of trials increases, so the more you sort of train your dog, in this case if you like, then the greater the associative strength is, which makes sense really, that's pretty common sense. There's some symbols in the equation. Delta V is the change in associative strength of the conditioned stimulus and the conditioned response. Okay, so that is basically the gradient, if you like, of the asymptotic curve. It sort of goes up, hang on, let me do it the way you're looking at it, sort of goes up, then plateaus. And then lambda is the maximum associative strength, which you can get, because you can only learn so much, can't you? So that's when it plateaus off. And then you have alpha and beta, which are constants. So this rescorla-wagner model is very useful at determining when an animal has completely learnt a behaviour. It's also useful at looking at the extinction of behaviour, or uncoupling. So the uncoupling of the conditioned stimulus from the unconditioned response. Okay? And that graph basically follows the same sort of shape, but just the other way around. So it sort of goes down like that. So it's still another asymptotic curve. But what you find, if you try and teach the animal again, right, then the rate of associative strength, so delta V, is much greater, so it increases. Okay, so it's much easier to relearn something than learn something from scratch, which makes sense, right? Okay, so that was all first order Pavlovian conditioning. What about second order conditioning? Now this is all about introducing an extra stimuli. Okay, so in the case of Pavlov's dogs, well, we're replacing the bell with a metronome now, because Pavlov for some reason went a bit more low-key. So when food was ready, played a metronome, dog salivated, right? And we're assuming there was no blocking taking place here. Remember what we were talking about with the associative strength with the bell being so strong that any other stimulus was completely ignored. We're assuming that didn't happen here. So we have a metronome being played, dog salivates. Then we introduce a second conditioned stimulus, CS2, and this is a black square. Don't ask me why Pavlov decides to do that. But anyway, so we introduce a black square to the dog. Okay, so then that was shown whenever the metronome was played. So the dog developed an association with between the black square and the metronome. Okay, and there was an association with the metronome and the food, the smell of the food. Okay, so if you only present the black square to the dog will salivate, because he's associated the black square with the metronome and the metronome with the food. Food's lovely, I'm going to salivate. Okay, it's quite clever really. Okay, so let's go away from dogs. What about insects? Can they be conditioned? Really? Well, yeah they can, apparently. And a good example is a study on bees by Dawson and his colleagues. So what they did a first order conditioning experiment to start off with. So what they did, they got a load of bees, and then they stuck fake bees, okay, or dead frozen bees, I don't know, and they stuck them on particular flowers, okay? They're probably fake flowers, okay? So they stuck dead bees on fake flowers, okay? And they let some real life bees observe what was going on, okay? So the bees saw that there were conspecifics, so members of its own species, on particular flowers. So then what they did, they removed the conspecifics, they removed the dead bees and allowed the real bees to fly in and feed on the fake flowers. Now the place where these conspecifics were, by the way, was on the flowers with a sucrose reward, okay? Because there are other flowers where the quinine, punishment, okay? So, what you found was that the bees went to the flowers which the conspecifics were on, which is pretty amazing. So they developed an association between the presence of the conspecifics, that's my Facebook, ignore it, that's the presence of the conspecifics and a sugary reward, a nice food treat. And if the opposite was done, so if the conspecifics were put on a punishment, so the quinine flowers, then the opposite response was shown. Quite interesting. So, in the second order conditioning experiment, the scientists wanted to develop, see if there was an association with a second conditioned stimulus, so a CS2. And here the CS2 was the colour of the flower. So here it was the green flowers which represented a sucrose reward, and it was the orange flowers which represented a quinine punishment. Okay, and the bees observed developing an associative strength between the conspecifics on these particular flowers. So they put conspecifics on the green flowers to start off with. Okay. So then the conspecifics were removed. That was conditioned stimulus 1. Okay. So then all they've got to go on now is flower colour. Okay. And what they found was that the bees went to the green flowers. Okay. So because they associated flower colour with the conspecific presence and conspecific presence with a sugar reward. Okay? Pretty clever really. Alternatively, if the bees learned that their conspecifics were associated with quinine flowers, then they could learn to actively avoid them and go to the green flowers. Okay? Pretty amazing stuff. I think you'll agree. And what are the ecological advantages of this? Well, it could be that if you see a conspecific on a particular flower, then you don't really want to go there because that little bugger may have already used up all the nectar, so you wouldn't get anything at all. So what we're seeing here is that these bees are maximising their resource exploitation based on this second order conditioning. Amazing. So this has made scientists think that actually this process of conditioning is actually simpler than we once thought. So we can apply Morgan's canon. Remember we talked about that in the first video. And the rescorla-wagner model predicts that the more stimuli you have, so the more conditioning stimuli, because obviously we can carry this on to third order, fourth order, fifth order conditioning and so on. So the more conditioning stimuli you have, the faster the association becomes. So the greater the associative strength, remember delta V in our rescorla-wagner graph. Animals can also learn two contrasting conditioned and unconditioned stimuli simultaneously. And a great example of this we talked a little bit about in the last video is the Sir and Per response of bees. So bees can be trained to extend their proboscis, so that's the Per response, proboscis extension response, when a particular odour is introduced. Because if they do, they'll get a sugary reward. They can also be conditioned to extend their sting, sting extension response, when a particular odour is used, because they get an electric shock. So they're given a little electric shock when that particular odour is introduced. So you can train a bee to either extend its sting when a particular odour is introduced, or extend its proboscis when a particular odour is introduced. So two different odours, but quite similar ones. So these bees have made two contrasting associations at the same time, and this is all due to different molecular pathways. Now if you think back to our second video, we talked about the Drosophila fruit fly. Oh, what a treat that was. And we talked about the 4 gene and the rovers and the sitters. Okay? Now, it's been shown through experiments that rovers learn more quickly, build greater associations when you try to condition them, than the sitters. Okay? So this is looking at the genetic aspect of learning. And this just shows that this form of conditioning is phylogenetically widespread and has evolved multiple times through convergent evolution. Now these differences are likely to be due to the different foraging strategies of the different morphs of the Drosophila. Now we can think of learning as a form of phenotypic plasticity, really, can't we? Because it's relevant in an ecological context. If we think back to our bees in the second video, which can change their phenotype based on the ecology of the environment, so if the colony is under threat, if the queen dies, then a worker can become a queen. There are certain cues which cause changes in the phenotype. Okay? And we talked about how this all could be due to epigenetics and all this kind of stuff. So these social insects are learning about the environment that they're in, and they're responding, they're changing their behaviour to counteract that. Now, if you're an animal in a relatively stable, non-changing environment, then perhaps learning isn't really that advantageous. If your environment is going to stay constant anyway, then you're pretty safe as you are. Instead, it's probably best to have some sort of innate behavioural strategy, so something genetic, basically, because this requires a lot less energy. Also, if your environment is constantly changing all the time, then is there any point in learning really? Because if you learn something one day, there'll probably be no point in learning it the next day because your environment would have totally changed. So it's usually at this intermediate level that learning is particularly advantageous in animals. Now, anything with its benefits can come with its costs as well. There are some costs to learning. It requires a lot of trial and error. So you're likely to make mistakes. It's very time consuming as well, so it may mean that you're more at risk of predation or competition from other species. Now there's a great study showing the benefits to learning was done in this weird organism to choose, but anyway, it was done in the blue gourami fish, okay, by Hollis and his colleagues, okay, and these fish make foam nests, okay, which float, and the female lays its eggs inside, okay, that's a bit of background. So what they did was, these males are very, very territorial, okay? They defend their patch against any intruders, okay? So what they did, they kept these blue gourami fish in the lab, and what they did, they introduced a red light whenever a rival male was about to appear, okay? So blue fish sitting in his tank, they don't sit, but anyway, red light comes on, and immediately a bad guy and rival male comes out the corner and jumps at it. And in this phase there was a barrier between them, so they could only look at each other, there was no physical contact. In the other group, there was a red light, there was still a red light, but the rival male came on very much later. You know, very much after the red light had turned on. So there was no way that an association could have been developed between the red light and the presence of a rival male. So then in the second phase, it was very exciting. These blue gourami fish were actually allowed to fight. So, red light was turned on, male comes in, and they saw whether the unconditioned or the conditioned males did better, or whether there was any difference between the two at all. And they found that there was. They found that the conditioned males were much more successful at fighting off their territory than the unconditioned males, therefore showing how important this conditioned learning is at survival. They also wanted to look at mating success, so instead of introducing a rival male, they introduced a lovely, glamorous, attractive female blue gourami fish. So whenever the red light turned on, pretty beautiful woman, well fish, came out, okay? It's the same thing, and they found the same again. They found that the conditioned males, which were conditioned to know that a female was soon to be coming around the corner as the red light turned on, they were more successful. So the conditioned males were more likely to show some sort of frontal mating display to these attractive females, okay, compared to if they weren't conditioned. So therefore, it's increasing their reproductive success. Brilliant stuff. Hope you enjoyed that. That's all I've got time for today. Next time we're going to be talking about recognition, how animals recognise each other. That's lovely, but for now, I've got to have a go around Sam about that washing up. I've got them all hyped up now. Ah, Sam, give us me again now. Oh.